Good afternoon to everyone, anyway, and welcome to this lecture. I estimate it's going to be about an hour and 10 minutes, and so there should be enough time allowing for questions as well. Before I start, a brief history about my career. I started my career in 1966 with what was then the GPO. I spent some 25 years with what became BT. And the latter part of that career was spent with British Telecom International, where I was responsible for signalling systems, international signalling systems, and a little known subject of echo cancellation, which I thought I'd got rid of until I moved into mobile. You'll notice from the slides as I progress that they are branded with Flint. And Flint was a company I co-founded back in 1999. After I'd left BT, I'd spent a bit of time, 6 years with Ericsson's as a systems integrator for them. And I founded Flint co-founded Flint in 1999 and was its chairman up until 2009 when I semi-retired. So a big thank you to my friends and colleagues who allowed me to use some of my own material, which is part of a training package which Flint produces, amongst other things. And I'm proud to say that Flint is also now a sponsor of the museum after I twisted their arms. Anyway, here we go, gentlemen. I'm going to attempt to tell you the story about how it all started and where I think it's going to end up. It's predicted that we're going to have a tsunami of data, and the worrying part about it is it's going to consume 1/5 of the total global electricity supply by 2025. So when people think about using a mobile phone, it's not without its implications. As you can see from there, it's going to get worse. But ironically, the industry has been mindful of power consumption from day one. And if only, first of all, it was worried about how long batteries would last in mobile phones. So a lot of techniques were used to optimize power consumption to conserve battery power. Those have now been extended even further. And 5G, its main objective is to reduce the power footprint in order to deliver this capacity. So they are going in the right direction. So looking at how it's going so far, market trends and data consumption, you can see the percentages of what were 2G and 2.5G and 3G and how they've been growing. This obviously the slide's slightly old now, but it's not far off because we did have a bit of a bump with a setback in the economy, and so these figures are actually, I've checked, they're almost currently just about right. And what with COVID, the implementation of 5G has, to a large extent, stalled the rollout. But no doubt that will pick up, especially given we've all become very familiar with using this type of technology now. Okay. So, in the previous slides, it was talking about ectobytes, and I have problems, like most people, getting your head around what this actually means in terms of zeros. So I had to put it up and show it to myself. For those who obviously might know, an ectobyte, as you can see, is 1,000,000 terabytes or 1,000,000,000 gigabytes or 1,000 petabytes. Someone said that it's about 5 ectobytes would actually encompass all the words ever spoken by human beings. How you come up with that conclusion, I don't know, but the idea is it's an awful lot of data and we're chucking it out at ever increasing rates. So where to start the story? I'm going to start the story further back than you would care to imagine, actually, because some of the characteristics of the history of communications have set the constraints in the mobile world. And you'll see as I progress why that is. So to start off, the basic communications, as soon as we got our head round electromagnetic theories and things like that, we soon applied it to the method of communicating over distances. As you can see here is a schematic of a telegraph, and though originally there were 2 wires, it was quickly learnt that you could do this over 1 wire with an earth return. So a majority of telegraph systems were 1 wire and earth return, and given it was a semi-digital code, its ons and offs, and so its signal and the quality of the signal and the degradation or attenuation of the signal could be quite severe before you lost intelligibility. And so the need to repeat or boost the signal was somewhat simpler. Instead, as you can see from here, you just got a simple intermediate relay repeater, and you just broke the section of line, and then you produce a fresh pulse, and therefore you get the same distance again. So you could bridge quite big distances, and really the noise component against the signal intelligence was relatively easy to contend with, providing you didn't get to the point where you had no pulse, so you couldn't drive a relay. So that was great guns until somebody decided, well, first of all, I forgot about it. So the other point, but as the network grows, these simple networks became congested, the appetite for communication between point to point. And so the early telegraph systems had very simple time division multiplexing. And there's a picture of a simple clockwork device here. Excuse me while I meet someone else. Which effectively enabled multiple users on a single wire system to time share that link and gave a slot to each of the users. So early telegraphic things had methods of repeating as well as methods of time division multiplexing that sparse resource, which was the 1 wire going to wherever and the number of people that needed to share it. Then we get something which enables the use of that infrastructure in a much simpler way. You don't have to be a Morse code expert, and it then opens up the field for the general public to use. So the first thing is, all right, we'll adapt the telegraph system as is, and we'll use this 1 wire earth return system. And to some extent that worked. It had the same sort of problems with noise and attenuation, but it wasn't too much of an early threat. But the device needed something else. It needed a receiver and a transmitter. The idea of talking and then pushing it to your ears and to hear the response made the duplex of it very much unuser friendly. So we had the beginnings of a receiver and a carbon microphone in series in the circuit. The thing that this produced, which was a side effect, which I'll allude to later on, is known as side tone, whereas the talker actually hears some of what he is actually saying, and some of the energy content is being recreated in his earpiece. This has the effect of making the talker lower his voice. And as an aspect of a mobile phone, you don't get side tone, and therefore people do not regulate their voice the same way as they do on a conventional telephone, because there is no side tone. Success, well, you can see here, it very, very quickly became, well, we'll have more connections, and because it was mainly overhead, you can see that the use of telegraph poles and the logistics of it became a nightmare. But they tolerated that up to a certain point until they had to compete, and ultimately, obviously, we get to cables, and you can see some of these towers. This is that tower is in a Stockholm exchange in Sweden, and the other picture is a 4,800 pair cable, one of the biggest cables that BT ever used, in terms of twisted pair anyway. So the early telegraph poles, single wire, earth returned, great in terms of use until someone decides we're going to have electric tram systems, and then the noise from these circuits got induced into the earth return systems that which included the telephone system. And so despite trying to sort of compete against it, there was no way the telephone companies could have avoid it unless they stopped using the earth. So they went back to using pairs of wires, and it became apparent very quickly that the best way to cancel out some of the effects is to put a cross in the overhead spans and effectively put a twist into the cable. Twisting the cable, as we all know, has an effect on the characteristics of the pair, and that in turn makes the circuit, or in this case the telephone circuit, subject to attenuation by the characteristics that are produced by a twisted pair. So what happens is you get resistance of lengths of cable. So you then pick, something, you don't use iron wire as they originally did. They use copper. So you can avoid resistance problems by improving your conductor. Then you have problems with the inductance or the insulation resistance, and you can improve that. But the other aspects, which is inductance and capacitance, just continually increased as the cable length just became longer and longer and longer. So the spans work against you. So the net result is that the attenuation on long circuits became quite severe. Enter a man called Oliver Heaviside. And Oliver Heaviside looked into the characteristics and said, well, what is it about the four characteristics, the resistance, the conductance, the inductance and capacitance, that I could vary with a view of trying to improve the transmission length of a cable? And after a lot of sort of mathematical theorizing, it became painfully obvious that the only thing that could be readily changed is the inductance, or the insertion of more inductance to counteract the effect of capacitance. And his solution was to put in series of inductance. In this case, it was 88 millihenries every 2,000 yards. And that had the effect of improving the transmission distance, but it also made the cable a bandpass filter. And one aspect about the whole of the transmission network or telecom network is the fact that it restricted the bandwidth to what's known as in the business as commercial speech. So therefore, the act of loading the cable to improve transmission length also restricted the frequency response of the cable from around about 300 hertz up to 3.4 kilohertz. And so you can see the graph there, the difference between a loaded and an unloaded cable. It had a quite sharp impact on the cutoff frequency, but nevertheless, it was very usable for the task of transmitting speech. So that's why when we all use the phone and people say, how do you know someone's using the phone? Well, mainly because it's bandwidth restricted. And listen to a radio play, they only have to play that trick of restricting the bandwidth to get you to believe that they're using a telephone. This bit of sort of characteristics and physics gets then transported into all the evolutionary steps that take place next, right up to the introduction of mobile phones. There's a bit about the formula and how we get to the bandwidth and the distance. You don't really want to know that. Anyway, so despite the improvement on the transmission length of cables, nevertheless, you still got attenuation. And if you wanted to go any sort of distance, you would have to have some form of repeater. So in the days of analog, it wasn't long before it became apparent that you needed further amplification, but the amplification with the use of valves, as it was in the early days, meant you had to take the two-wire analog circuit that you were using and split the transmit and receive speech, and so you could amplify it in one direction. And this diagram shows the fact that that's what was done. The passive component that actually allows you to do that is a thing called a hybrid transformer. The hybrid transformer is a schematic of a hybrid transformer, and basically allows a two-wire circuit to be converted into a four-wire circuit, but it requires a balancing impedance to cancel out or to balance the impedance of the two-wire line against the transformer circuitry, so you get the same currents flowing in both directions. The only problem with this, if that matching balance is not correct, you end up with an echo loop. So, yeah, I'll put it in this. You get the distant person talking over this will hear his own voice reflected back if for any reason the line is not balanced against the matching impedance of the hybrid. Now, in the early days, if we were talking about analog, in a place in a country like the UK, the propagation delay on an analog circuit was only about 7.2 milliseconds. So not a problem, and you would perceive that reflected side tone, that echo as side tone. As we progress with digital techniques, we unfortunately increase the propagation delay, and if the propagation delay on a round trip call goes above 24 milliseconds, or sorry, 24 milliseconds up and 24 milliseconds return, you get to 48 milliseconds. The brain at that point can almost determine that there is some echo. And in fact, when you get to 50 millisecond round trip delay, the brain says, yes, this is echo. And at which point you would have to do something about cancelling the echo in order to make talking on that circuit easier. I've got the issue of, so if we now look at what happens next, we progress with the telephone development, and ultimately we introduce digital transport systems throughout the telecom infrastructure. And you can see we've got the same circuit again with a hybrid, where the circuit towards the two-wire telephone is still analog, but beyond the hybrid, there's an analog to digital conversion. And because now we've got a digital delay as well, we have an increased likelihood of side tone and echo. In the UK, and I was part of the Echo Forum, we ensured that every transmission path from one end of the country to the other never went through more switching stages than would increase the overall one-way delay beyond 24 milliseconds. So we made sure that every call routing path had a maximum end path delay of no more than 48 milliseconds via the hybrid, because you cannot protect your circuits against on an international route, and therefore most international routes you will exceed these limits, and therefore all international circuits have to have echo cancellers on. And I'm just showing that there, and what I've just said about 50 milliseconds recognises echo. So slide covers what I've just been talking about. So now we finally get to interworking mobile phones with what was predominantly the major communication medium, which was still the fixed line. So on the early introduction of mobiles with the GSM codec for digitizing the speech actually had a one-way speech transmission delay of 90 milliseconds. So if the caller was to then call a fixed line phone where there was a hybrid involved, the chances are, if it wasn't balanced correctly, you would get echo, and there'd be another 90 milliseconds, so there'd be a 180 millisecond round trip delay, and you would get severe echo on a mobile call. And therefore, because the UK network didn't have any echo canceller requirement, every mobile network had to fit echo cancellers. And this is where I entered my career in mobile, because that was one of the first problems I was asked to address in terms of using and where to place echo cancellers in the network. Ideally, it should have been put in by BT, but BT's attitude was, you created the echo, you cancel it. Enter another concept which is going to affect the story, and that's pulse code modulation. Pulse code modulation, we partly alluded to it in the previous slides with the idea of digital conversion, and this is about the digital conversion. How did we actually take the analog waveform and convert it into a digital signal? From the history of line and cable characteristics, we know that the bandwidth of the speech we're dealing with is restricted nominally to a 4,000 hertz, and therefore if you understand sampling methodologies, providing you sample at a rate twice as high as the highest frequency you wish to transmit, you can accurately recreate the waveform. And these three diagrams here show that principle of the first one, where you've got your speech frequency, and if you double the sampling frequency, you can get a more or less crude representation of it. You can oversample and go 4 times, but you gain nothing in terms of the intelligibility of the waveform that you're trying to transmit. If you undersample, as in the case of the bottom graph, you see that you start to lose the original waveform pattern to the point that you can't reconstitute it. So the standard sampling rate for speech in digital systems is 8,000 times per second, which is twice the highest frequency, which we just said, which is 4K. So if we then look at how we do this, we sample, and we basically sample at the sampling rate, which is once every 125 microseconds. We then quantize the measured voltages and produce a encoding 8-bit representation of that quantized signal. And it's that bit pattern which is then transmitted to line. At the receiving end, that bit pattern is then collected, and you recreate the crude representation of the waveform, and then you pass it through a low pass filter, and we get back more or less the analog signal that we originally started with. So that is, in essence, the digitization of it. But the interesting part about this is, what do you do with all the spare time between sampling one bit of speech and then 125 microseconds later, you do it again? Well, the simple answer is you can get another 31 circuits in there. And this diagram here shows you the frame structure. So in the middle of the picture is our bit of speech, which for circuit number 1 in this particular case. And the yellow box is, well, that's my first sample. And I put my first sample into a frame which I'm going to transmit. The time slot that's allocated is only 3.9 microseconds, and each pulse, each bit of the 8 bits has got a duration of 488 nanoseconds. So we've got this burst of bits and then nothing other than other time slots of other circuits until we ultimately get back to channel 1 again, 125 microseconds, and then the green sample is put in the next speech frame. So you can see here, we've got the beginnings of not only digitization of analog circuit, but we've also got this early thing that occurred with the telegraph, the ability to time division multiplex a cable. This idea obviously took grip as the price of copper went up, and before we got to the solution ultimately of using fibre and fibre optics. And so as BT and many telecoms companies throughout the world struggle with cable costs, the answer was to invest in the digitisation and the reuse of the existing infrastructure, thereby multiplying the capacity at a basic rate anyway, at least on this is an E1 frame, you could actually multiplex it up a lot more because you could take it up 8 times or even 32 times and get a great increase in the usage of the existing copper infrastructure. It also enables you to contemplate the idea that you could possibly switch time slots and therefore have the concept of being able to route a call over different systems by shifting time slots. So the top part is a space switch where you simply take an input and you cross-connect it to another output. And the middle part of the diagram shows you speech samples arriving in a time-space switch where you can reorder the time slots. And then the final diagram is what's used predominantly in most digital systems and still is the major backbone of the BT's national network, is a time-space time switch where you're taking in E1s and you rearrange the time slots and systems and you can reorder them and transmit them to the required destination. So you can switch between the PCM, the E1 systems, and change the time slots. This capability becomes the basic building block of all of what I'm going to talk about next until we arrive at IP. So, overview of how we're doing for time. 32. Okay. First handheld phone was demonstrated back in 1973 and really was a culmination of the problem that even allowing for the fact that we could use radio, there was not enough radio spectrum ultimately, if everybody wanted to use a mobile phone, to have enough bandwidth to give everybody a communication to talk, or at least the bulk of the people to talk during the busy hour. So the concept of a cellular phone where you could restrict the transmission or the cell that you're transmitting into to a limited area and thereby use the frequencies you're using in one cell, and providing you put enough space between the cells, you could reuse those frequencies. So the concept of having cellular radio was to reutilize the asset which was in short supply, which was radio spectrum. And here we got a table of mobile generations. The concept of generation didn't exist until we got to 3G, and then everything retrospectively was given its place in the evolution of it. So 2G and 4G really sort of got their naming after the licensing of the third generation mobile. So, but looking back retrospectively, 0G, the non-cellular type of mobile phone, was first available in the UK. Excuse me, while I just move this out of the way. Sorry, John. That's better. It was first in part used in South Lancashire, and it started in 1959. And it was followed in the 1970s by System 2, which only had 9 channels. I don't know how many channels System 1 actually had, but and it was a 1-mast transmitter, and therefore you relied on a lot of power for the mobile. Well, it wasn't really mobile, it was a transportable that you fitted in the car with lots of large batteries and a big transceiver. 1977 saw System 3, which had 55 channels. These are all analog, by the way. And it wasn't until 1983 we got to System 4, which was a 95 channel, fully automatic. That means you could dial it. The previous systems, you needed an operator, and it was a voice-only service. As I just discussed, the first analog system, or analog cellular system, was during the 1980s, but these all shut relatively relative to the deployment of the other systems, which made better use of spectrum in 2001 and Cellnet in the year 2000. What's happening there? All right. Okay, so that was an analog system, and we went on. The first digital system was GSM. It was at my point where I entered into mobile phones, and the first ones were deployed in Finland, and could do voice as well as data, but it sent data over the voice switch part. There were different variations of the technology. So if you went in different parts of the globe, they all use different modulation techniques. So as the industries globally realized that it's all very well having mobile phones and cellular mobile phones, but it's not going to really get together as a system where you could move your phone around the globe unless we all started to talk. So there was an attempt then back in the 80s and 90s for all the industries and the operators to start looking at some standardization so that we could all cooperate with the manufacture of equipment and devices. We move on to the fact that it became very apparent that data was still required as well as voice, and the 2G networks were evolved into 2.5 and 2.75 with the adding on of what was known as general packet radio services. And I'm going to cover those in a bit more detail later on. As data then increased even further, the third generation went into another gear of optimizing mobile networks to take on the task of carrying more data. The industry did not actually sign up to the idea of calling the next iteration of mobile phones as 4G. It called it long-term evolution. And my involvement with it, we always talked about long-term evolution and long-term evolution advanced systems. But marketing made it a 4G sales pitch. And so a lot of what was called 4G in the industry was known as 3.9G because it really wasn't the full-blown capability that everybody was talking about. And to some extent, 4G never really got going as it should have done. until it was caught up by 5G developments, where they looked at how they were using spectrum in 4G and thought, oh, we can sweat this asset even further. So we're now going to go into a bit more detail about that particular part. I mentioned briefly, I'm going to skip past these slides to save a bit of time, the idea of standardization. The group which was formed during making 3G occurred was called the Third Generation Partnership Project, and it brought in everybody that had a vested interest in the development of mobiles, from the handset manufacturers to the infrastructure providers and the operators. And that went across the globe. And it's 3GPP group, which went on to develop 4G and 5G, as you understand it. There's some of the timescales of how the developments went, but I'm going to cover that in more detail with some other slides. But you get a general idea that there has been an evolutionary gear change and trying to sweat the radio assets. This slide is a bit better because it gives you an idea about how the industry was looking at it. It was doing it in 10-year chunks. It was doing, so the 80s was 1G, and by the time it got optimized and fully deployed, they were already thinking during that time about the next generation, and then the next deployment from the 90s to 2000 was 2G, and like so on and so forth. So we're at this point now at 2020 where 5G is almost ready to go. The standards are still evolving, unlike 4G, which was fairly well standardized before it got implemented and is still being implemented as such. 5G is still taking advantage of the technological changes, particularly in processor capability, as to what they can envisage and what they can include in its lifespan. There's another slide just showing all the relationships of all the bodies that's making up the standards group. And some of these other groups, particularly the ITU, the International Telecommunications Union, to a large extent has become sort of the subservient member of 3GPP. But the other big group in here is the Internet Engineering Task Force, because as the mobile networks head towards an IP infrastructure, they are more like, more akin to the IFTF in terms of their thinking and methodologies. Anyways, a bit more there. Let me skip that slide. So we need to cover some quick concepts and terminology. We've all heard about the spectrums and different use, but within the industry, there is the concept of unlicensed and licensed spectrum. Governments like licensed spectrum because they can extract loads of money. Typically, the best example of that was the 3G license sale, which extracted in excess of £22 billion from the industry just to deploy or have the privilege of deploying 3G infrastructure. Whereas the operators, if they could use Wi-Fi, they would, because it's unlicensed. You can't really use Bluetooth, because Bluetooth is restricted in terms of its use because it's near communications. It's not designed for wide area use. Albeit, I have now seen people who are extending the use of Bluetooth up to 100 meters, and it does encroach into some of the space that will be probably used by 5G technology. Nevertheless, that's how it stands at present. These are the spectrums. There's a better picture here about what's actually happening with the existing mobile spectrums and where the new spectrum being called for by 5G. The irony of it is that 5G does not use exclusively new spectrum. It effectively is reworking all the existing spectrum. So its modulation and use techniques will ultimately be gained from the relinquishing of spectrum use for 2 and 3G as they slowly become defunct. Even the old TV channels, and then for those you noticed that 4G bumped into that, where the 4G spectrums were actually encroaching on the old TV spectrum. The most interesting part about the modulation techniques and the use of spectrum is initially it started off with omni-aerials where the signals just went in every direction. And when we got to the cellular concept, we needed to beam the aerial so that they became more sectorized. So they used Yagi arrays, and but now 5G is going to take it a stage further with beamforming, with the idea that you are going to steer the radio transmission and optimize the power consumption and also track the mobile by steering the transmission directly towards the user. And this way you can save on battery power for the mobile. Okay, I'm going to cover some other bits and pieces which are to do with the SIM card. SIM card, what is a SIM card? SIM card basically is a computer which actually does the authentication algorithms and holds some data about the mobile subscription, but its predominant function is to authenticate the network against fraud and interception. And initially, the SIM card was an integral bit of software and hardware which couldn't readily be changed. With the advent of 3G, 4G, and 5G, there was a thing called a USIM, which didn't look physically much different from the original SIM. The voltages were changed and the capacities were changed, but it enabled the fact that the chip could actually have different software loaded onto it, and therefore the functionality of the SIM can be changed, and therefore the phone. So the phone, when you plug this SIM card in, the operator can load down operator-specific software, which will change the performance of your mobile to match the functions and features they wish to give you, as well as doing the authentication part. Okay, this gives you just an idea of the capacities inside here. The SIM cards have gone from 32 kilobits to 128 kilobits worth of storage. They're even bigger than that now. Predominantly, they used to keep the mobile networks you were going to roam to when you went to different countries. The predominant use. The idea of using it to store contacts has been largely superseded by smartphones, which have got greater capacities to do that. We need to talk about how the network identifies itself and the numbering scheme, which you need to understand. Unlike the country code that you dial, mobiles have got a thing called a mobile country code. The UK's got 234 and 235. You'll see the significance of this as I go through it, but you can get the idea that there's another numbering code for mobile networks independent of their national dialing codes. And then obviously, once you're inside country, you need a mobile network code. So depending on how number of networks you've got, in the UK, we've got Vodafone and O2. Both have obviously got a mobile country code, which is 234, but we've got these country codes, network codes of 10 and 15. You can see other countries there. This helps the mobile work out what country you're in, as also whose network. So these are two key component parts of a numbering scheme, which I'm going to expand. The thing that makes the mobile phone known to the network isn't the number that you dial. As far as the network's concerned, the only number it knows is the International Mobile Subscriber Identity. It's made up of three parts. It's made up of the mobile country code, which we just discussed, the mobile network code, and then within that network, a mobile subscriber identification number. These three components make up a maximum 15-digit number, which is known as a E212 number. And it's this number that the network uses to communicate with the mobile and how it builds it, how it and knows where it is and what it's doing. The number you dial, which we're going to cover in a second, the mobile subscriber international subscriber directory number, integrated services digital number, sorry, is what's known as an E164 number. And again, it's broken up into its component parts. It's got a country code, which we all recognize, the 44, the network national dialing, the national destination code, the NDC, and then the subscribe number. So it's got a similar structure to the IMSI. This is the number that the mobile is known to by us outside of the mobile network. That's the thing we dial and how you route the call to the mobile network. But once it gets to the mobile network, it only communicates with the IMSI. The other component part of this story is the identity of the mobile. The mobile has got its own equipment number, so the International Mobile Equipment Identity, and this can be used to track the mobile as much as the other two. So you can trace the phone's use by MSISDN, its dialed number, its SIM card number, or the mobile identity. These three aspects, and if you disassociate the two, each component part can be tracked in its own right. So if you were to change the SIM card, the network would know that you're using that mobile phone with another SIM card. Radio network cells. As we discussed earlier on, we've got a restriction in spectrum. So the idea of having a cellular network with fixed transceivers in a cell, and the size of these cells depends on the deployment area. So if we're talking about rural areas, the cell size can be 35, 40 kilometers in radius. If you get to the likes of a cell site in Fleet Street, they can be as small as 100 meters, and you could change cell sites just walking up Fleet Street. The terms used to describe these types of various sizes of cells are called macro, which was the first one I talked about, micro, pico, and femto cells. And we have also the concept of umbrella cells for excess capacity. So umbrella cells can extend and give extra capacity to cells which are in congestion, or in the event of a network failure, provide coverage when the small cell's gone down. The idea of using multiple frequencies, if you had an omni cell, you would put the transmitter in the center of the cell and then allow it to radiate in all directions. The reality is, if most people, as you drive past the cell site, you would see a triangular infrastructure, either on top of a building or on top of a tower, with the sectors pointing at the apex of a cell site. So if you look at the other diagram, you can see that these cell sites are at the corners there and beam into the cell, and the numbers adjacent to them reflect the frequency bands that are being used. So if I just can't see it in my picture, but you'll see that some of those frequencies repeats do actually repeat. And so it's this color coding or frequency of reuse which has enabled the cellular system to get the capacities by either having big or small cells, and we'll cover that in a bit more detail as I carry on. Sorry. Obviously, the cells need to be identified, and the cells are grouped in into location areas. And these pictures, I'm going to quickly go over here, cover the concept of giving the cell an identity and then placing it inside a location area. The idea of location area is to work out roughly where the mobile is in the event of trying to communicate to it. You don't remember a specific cell, you just remember that a mobile is in a certain location area when it comes to paging it and passing information back to it after it's made a request. There's the concept of routing area. Routing area is used by the data part of a mobile. So we've got location area, which is to do with voice, and routing area, which is to do with data. I'm going to quickly go through here. When we changed from 2G and 3G, we also changed this labeling of areas. Instead of calling it either location or routing area, they're called tracking areas. So when you talk about the cell identities in 4 and 5G, these are tracking areas, not. But the principle is applied again. It's to rationalize the number of cells that you need to communicate with in order to page a mobile. The cells also have a unique global identity. So not only are they within a location area or tracking area, they're also uniquely identified. And that sort of information gets put into your call data record when your call is being made. So if you want, it's possible looking at the billing records to work out exactly which cell you were associated with when you made the call. Finally, there's this issue about color codes where it's if you're on a landmass which has multiple countries where mobile networks actually butt up against one another, the cell sites also have what's known as the color code, which help you to distinguish not only its identity for the purposes of roaming into, but also the fact that it's in a different country and there's a different network code. So it's got this thing called a BISIC, which is an additional broadcasted bit of information that tells a mobile phone that you're changing not only mobile networks, but you're also changing countries and therefore roaming into another network. Finally, cell breathing. As a cell takes on more customers or more mobile phones attached to a given cell, it can actually contract its cell size if the quantity of people increases. So it helps regulate the load on the cell. So when there's low load on it, it breathes outwards and will allow communications over a larger distance. But if it's in congestion where the number of people have congregated, it will shrink in size. So there's a lot of dynamics going on here with the cells as you're using them. It's not fixed. What am I doing for time? 57. Okay. So, talking about types of modulation scheme. It's the mobile networks all have evolved different modulation schemes, and this is all to do with sweating the asset and getting the most out of the bandwidth or the spectrum that you've been allocated. And they've all been given these generic names of GRAN, UTRAN, Enhanced UTRAN, and the 5G is called 5G New Radio. But I will cover these in a bit more detail as we carry on. So if we look basically at who's using what, GSM and its component parts use GRAN, 3G, which is UMTS in my speak, uses UTRAN, and evolved packet system, which is 4G, uses EUTRAN, and so does 5G. So what does it actually mean? Of the spectrum that we've been allocated, the radio access technology, RATs as it's known in the business, uses spectrum in the following ways. So if you were talking about the original 1G analog mobile phones, it's one user, one frequency. So it's a simple frequency division, multiple access. When we got to 2G, we can have one frequencies and we can time division multiple access this. So it's a TDMA access. When we got to 3G, they had a rethink and they went for wideband co-division multiple access, whereby everybody uses the same frequency, but we encode each bit transmission with a cipher key, which effectively encrypts the bit pattern. So only if you recognize the bit pattern can you actually decode the message. And finally, 4G and 5G uses a combination of all the three previous techniques of frequency division, time division, as well as the concept of orthogonal frequency division multiple access. So you get a general idea that it's getting the most out of the spectrum, which is what this has all been about, not so much the phone network itself. In 4G, the difference is it uses orthogonal frequency division multiple access on the downlink, but it uses single channel frequency division multiple access on the uplink. That's mainly because the mobile can only support a limited number of antennas. So it's only got one antenna. So, but 5G phones, that will change and you will get orthogonal frequency division multiple access on the uplink and the downlink. So it's different for 5G. This is just a bit more description about 5G, it's a bit too much. So let's look at some of the modulation techniques. Obviously, we've got amplitude modulation, frequency modulation, phase modulation, and for most of you, hopefully, if you take a basic binary signal, you can see you can use these different modulation techniques. Amplitude is simply turning it on and off to represent your binary code, or in the case of frequency modulation, just varying the frequencies. But the more interesting one is the phase modulation, where you deliberately change the phase and amplitude, as you will see, in order to convey the bit pattern. And it's its last modulation technique, which is the one that's been exploited the most, as you will get to see. So TAX was, as I said before, frequency division multiple access, one phone, one frequency, and therefore you can see you can quickly run out of frequencies and capacity. And again, its speech bandwidth was 4K. If we look at 2G, we've got the idea of these multiple users and one frequency, and the basic structure was 8 time slots per frequency. And obviously, you've got 8 time slots going up and 8 time slots coming down. And there's a deliberate shift of 3 time slots between the up and the down in order to differentiate and help the phone synchronize to the base station. I was going to talk about this, but I'm running out of time, gentlemen. I'm not taking any questions. So if we take what happens with co-division multiple access, with the wideband version of it, if you look at the user data, which is a top trace, it is, let me just move this out, sorry. The user data is exclusively ORed much the same as a Lorenz cipher machine would have done, a unique code, and the end result of that is what's transmitted on the bottom. So at the other end, providing you exclusively or the same bit pattern, you will get the user data back out. But everybody's transmitting on the same frequency at the same time. It's only this coded part which helps you sort out the difference between one user and another. You can actually have 255 simultaneous users per frequency with this configuration. So let's just look at how some of this modulation is achieved. We have binary phase shift keying, which is basically used in 2G, and when it got enhanced, we had the quadrature phase shift keying, which is a 2-bit variant. And then as we moved into improvements in 3G, we went to 16 QAM, which is a 4-bit constellation. And then as we move into 4 and 5G, we're going into 64 QAM. Well, in fact, we're going a lot further than that. We're doing 128, 512, 1024. And you can see, as I show in this diagram, every phase shift and amplitude change represents a different bit pattern. And as you progress in time, you're simply altering the amplitude and the phase to convey a 4-bit pattern. So you take your data, you map it to the bit pattern you wish to transmit, and that's what you transmit. You transmit your phase and amplitude in order to convey your intelligence. The only problem with this is it's obviously susceptible to noise, because the more crowded this constellation map becomes, the more difficult it is to differentiate between the different levels of amplitude and phase shift. This is good in radio environments which are nearby, and it will be extensively used in 5G on short ranges, and here QAMs of 128 and excess are contemplated to optimize the bit rate. Just further detail on this sort of information. And this just tells you the number of bits per symbol you're getting, which I think most of you might know. Hopefully. I think I've covered that. Just there's more of that. Anyway, this slide here just shows you another complication to the story, that the spectrum that we all use for the mobile phone networks is caught up in the regulatory arms of each of the continents that actually license and let you use the spectrum that mobile networks use in your country. The net result of that is a mobile phone not only has to adapt between what we've been discussing, the ability to support 2, 3, 4G and 5G, but they also have to understand that the frequencies in each of the countries and the modulation techniques, particularly for 4G, which can use frequency division multiplexing or time division multiplexing in different ways, has to be known by the phone. Skip. The interesting part about data rates, and I will just look at the right-hand side of this table particularly more, is that LTE is looking at a maximum down rate, bit rate of 100 megabits per second with a 50 megabits per second uplink. With the advent of 5G, that's going to go to 20 and 10 gigabits per second. And the other interesting point is the latency in the network. How long you have to, the inherent transmission rate between the infrastructure and the mobile device. And it's considerably faster on 5G, mainly because it's anticipated that it's going to be used in real-time applications such as vehicle guidance and the like. The other aspect that's been taken into consideration with 5G is the speed at which the mobile could be traveling at. Most of the testing that I was involved with mobile phones was happy with if you could do a handover at 70 miles an hour or 80 miles an hour going around the M25. We're now looking at mobility and handover capabilities in excess of 500 kilometers per hour. While we've been talking about that, the codecs, we talked about the speech. The speech was restricted originally to this 4 kilobit bandwidth, but with the advent of higher bit rates, the concept of having better quality speech has come about, and the bottom part of the slide talks about adaptive multi-rate codecs, wideband codecs, which will give you near hi-fi, and it's anticipated when we go into 4 and 5G that we will go beyond wideband voice and we will go to super wideband and full wideband, giving you a virtual presence in terms of sound quality that you could receive at a mobile, or indeed transmit from a mobile, which is not what it's like at present. It is interesting to note that 2G and 3G only carry voice now in a circuit switch domain. 4G and 5G have to, if you make a voice call, it drops back to 3G or 2G. Some mobile networks are now doing 4G voice, but in fact it's voice over IP if you actually look at what's going on. And how do you keep the network synchronized? The networks, in order to keep all this timing and coordination correct, you need a high degree of accuracy. So the oscillators, which feed out from the core of the network and in turn to the peripherals of the network, to the base stations, require an accuracy of better than 50 parts per billion. You can see the different rates in here. I have a love-hate relationship with frequency synchronization because it's the pain of many a fault in the network when it doesn't work. And here's some of the distribution techniques, depending whether you're a 2G, a 3G, or a 4G. The synchronization is either fed out through time division multiplexing or asynchronous transfer mode, or in the case, as we've got to now, IP, and therefore, but IP intrinsically is not synchronous on an end-to-end basis. It's synchronous on a link basis, and therefore to get synchronization over, you need special signaling at Ethernet level to get the clock signal from an IP core out to the base station. Okay, how am I doing? Gentlemen, I'm concerned about the time. It's 17:12. I've probably got another 15 minutes to go. If you can bear with me, if you're okay. Yeah. Okay, so a 2G network. Here's a basic infrastructure with the base stations, base station controller, the BSC, and a mobile switching center. And then a gateway MSC, and then you connect out to the PSTN, the public services telephone network. The boxes, as you want to look at them, there's more than one of these in the network. Obviously, if you look at the number of base stations, in order to cover a UK network, a mobile operator deploying base stations in 2G would need in excess of 30,000 base station sites. Because most of them are with a triple base station, where the tower supports 3 cells, the physical number of actual cell sites or cell towers is about 10,000, but there are 30,000 odd cell sites. So when you look at the BTS part, just look at that and say, right, well, I've got so many cell sites and they're connected, typically 500 to 600 odd BTSs are connected to a BSC. So you can there see there's more BSCs, and then each MSC has approximately 2 to 3 BSCs connected to it. And in turn, the number of MSCs connected to a gateway MSC, the gateway MSCs are from the transit layer across the country, and also the gateway for incoming bound traffic from other networks into a mobile network. You'll notice that all the interfaces have got letters on them, and these are the protocol interfaces which help communicate, standardize the communication. The other elements here, the visitor location register and the home location register, the HLR, deal with mobility tracking and subscription. The other boxes, the authentication set, the AUC, deals with challenging the mobile and the SIM cards in order to make sure that you are valid, you are a registered user on the network. The equipment identity register, which was installed mainly to prevent fraud of stolen mobiles by checking the equipment identity, which I discussed way back, the IMEI, could have been used to stop the fraud in stolen mobiles. But the EIR now, the equipment identity register, is used predominantly to track software variants in mobiles and ban or block mobile variants which are no longer supported. So the EIR was originally designed as a fraud management thing for detecting stolen mobiles, but its use has been long misused effectively. Anyway, I've dealt with this before about the radio. It's actually 2G is time division. We've talked about that. But if we actually look at the time slot for a 2G infrastructure is 4.615 milliseconds, and this is a breakdown of an individual time slot, which is 577 microseconds. And as you can see, it's a short burst, and it provides enough bit rate to support 13 kilobits per second, which equates to roughly 20 milliseconds worth of speech. So each burst that goes up is representing a burst of speech. And so the mobile, whilst it's playing back or transmitting data, is doing other functions like looking at which cell it's on, checking the signal strength, doing a handover, and then getting back and doing the speech. So it's multiplexing itself between transmitting speech and handling the call. This is part of a bigger frame structure, but I'm running out of time, so I'm going to rush past this. But in order to see what happens with a call, voice call, it's interesting to see that the codec in the mobile is transmitted to the base station. It then is optimized and transmitted to the BSC, and the rate then is changed by a transcoder into the 64 kilobit, which is a basic time division multiplexing basic rate channel, and then that's transmitted across the network to another MSC or maybe out to the PSTN, and then the transcoding goes through and back out to the mobile. You can see that just to handle speech, there's a lot of transformation and bit conversions that go on in a normal circuit switch call. With the advent of the desire to transmit more data, other nodes were added to the network. So the original network I showed you with the BSC and MSCs, you've now got plumbed on underneath it these other nodes called SGSN and GGSN. There's a support, GPRI support node, serving GPRI support node, and the gateway GPRI support node. These enable the time slots we've just been talking about not to carry voice, as previously implied, but actually to carry direct bit data at bit level from the mobile into the IP network. So what people don't appreciate is the fact that the network is schizophrenic. It actually can do two things at once. It can handle data and voice simultaneously and transmit component parts, either a time slot for speech or a time slot for IP across the network simultaneously. So this is what happens when we had 2.5G. And this gives you an idea of the protocol structure on the interfaces, where your application data is put in at the top, so the actual bit of data you want to send, and then it's enveloped, put inside an IP envelope, and then it's put inside a subnetwork dependent convergent protocol, and then a logical link control, and then a radio link control, and then a medium access control. And you can see that these different protocol stacks work between certain legs of the path. They're not end to end. So your message is only unpacked to a certain level and then relayed to the next part. And it's only when you get to the destination that the whole message is then unenveloped and then read. This is what my job was conformance testing and compliance checking of every vendor who produced these protocol stacks. And I earned a fortune out of it. Anyway, keeping mobiles on track in mobile locations. So what actually happens, now I've got a network here, as the mobile moves from cell to cell, it does a location update. As it senses that it's moved from one location area, that's a group of cells, to another location area, it tells the BSC it's just visited that it's changed location areas, and transmits and sends a message ultimately to the home location register to update its location. And this is an overview of that, of the mobile saying, right, location update requests. It requests its identity, you get an identity response. It then sends a map message right away through to the home location register with its IMSI and its mobile identity. It cancels where it was previously visiting in its VLR, and then inserts all the data that helps the mobile function in the new visited MSC, and then the mobile gets a conversion. So this is some of the signaling load that's going on without the phone ever handling a call or any data, just moving around. There's a constant barrage of mobile location. If you're moving around and you change location areas, if you stand still long enough, you get a periodic location update. Again, there's an idea of the protocol stack involved in this, but we're running out of time. And what I was going to show you here, that at certain levels, you can actually pick out the bit patterns. And in the case of a map message for a location update to an HLR, in the list there, you send the digit 6, the binary equivalent of digit 6. So we're only talking ones and noughts here, gentlemen. This whole thing is a streams of ones and noughts. There are nothing else. The currency of this is binary. I've not got much time to do that. The 3G network. The 3G network arrived, and basically 3G was not a change in the network. We still had a BSC and MSC and the gateway MSC and the SGSN. We just added a thing called a radio network controller. So when everybody talked about 3G and wonderful, and everybody got new phones, the mobile operators only changed their radio access. They did not change their core infrastructure, which is probably a bit of a surprise to most people. It was a radio access, sweating the radio access. All the rest of it remained basically the same. We've dealt with that before. But as things progressed, the nodes or the boxes we've been talking about became further congested in terms of processing power, and it became obvious that instead of having a monolithic architecture, it was important to layer the structure of how the call was controlled and more to the point, to separate the user plane traffic from the control plane traffic. So one of the first upgrades to 3G was to split the intelligence of the network and the transport layers. And this was done live in networks across the globe, where the infrastructure, particularly the core network for the voice, was split into its component parts, first of all. And at the same time, we started to change the transport between them. Before that, all the connections between the nodes was done with TDM. It then moved into ATM and then finally into IP. And the colors on the links are reflecting the changes in the transport layers. Release 5, we finally migrated all the interconnections between all the boxes retrospectively and split the circuit switch into an IP backbone. There was some rationalization of network. This is, unfortunately, I can't go to this. This is actually T-Mobile's network before and after a rationalization where they, which I was responsible for dealing with. We added on here some other functionality, a thing called IMS, which is the beginning of this IP multimedia subsystem, which is beginning to change the way we transport the concept of voice across the network. I'm trying to get the next one. The next one. The next one is we finally also split the user plane and the control plane for the packet switch side. So we've got, where we've got an SGSN and a GGSN, that's 3G technology. When 4G came along, that is the 4G, the EU TRAN, has got split architecture for control. It's the MME, mobile mobility entity, and serving gateway functions are the same equivalent as what's in the SGSN above it, but the things have been split. You'll also notice that the 4G network has got no connection to the voice component. There are, unlike the RNC and the BSC, which are interconnected to both network elements in the top half of the picture, 4G has got no connectivity to the voice and ultimately to the PSTN. If you want to make a voice call, you drop back to 2G or 3G, and you can dynamically do that. 5G arrives, and 5G, again, is another node, a radio access change. The 5G is piggybacking on the 4G infrastructure. It has not, at this point, got its own discrete network, albeit it has been defined. And again, there'll be a further split in the boxes shown on this diagram, which subdivide that even further, because up until now, all of this has been on proprietary, purpose-built computing platforms. And now...
You've not got the slide updates. I think you've gone on 2 slides. We're still on 3G release 8, 10, and 11.
Oh, sorry. Yeah. Sorry. Thank you. Yeah. I haven't got a slide for that one, actually, Peter. Thank you. But what I'm trying to say is they haven't... the network nodes are going to be software defined. So they can go on out into the market, and network function actually is going to be virtualized, and therefore they can buy any hardware and load software functionality onto the nodes. So whilst these were built originally by dedicated suppliers of telecom infrastructure, the infrastructure is moving away into more generic computing platforms. What I haven't discussed is how your Wi-Fi access gets in there. A Wi-Fi hub comes via the broadband network, goes through a security gateway, a home node B gateway, and then connects to the nodes we've been talking about, this SGSN, GGSN. So case people wondered how their mobiles work with their home hubs, that's a very quick picture of that. There's improvements in antennas. I think they're self-explanatory. What I want to get onto, gentlemen, is the very last part, is what's going to happen next in terms of evolution, and that's the network function virtualization, which is what I've been discussing, software-defined networking and cloud-based services, and further separation of the user plane functions and the control plane functions. There's an interesting development called network slicing. Network slicing enables a network to appear to be a different network for different users and turn effectively mobile networks into a form of rail track, where a number of service operators will rent or use the infrastructure to have their network. And of course, at present, everybody's quite possessive of their infrastructure. But as the cost to maintain and deploy ever-evolving networks becomes more expensive, you'll find that mobile network operators will cooperate in implementing network infrastructure, which then they will resell or license to anybody who wants to become a mobile operator. This is quickly just showing you where the 5G infrastructure is hooked on the evolved packet core, which is a 4G. Ultimately, it will have a standalone connection and will have its own 5G core, at which point someone might have thought that we would not retrospectively have a phone that could do all networks, i.e. 5G, 4G, 3G, 2G. It's too onerous to make a phone carry on supporting all these legacy infrastructure and protocol types, albeit that with the idea of network virtualization and software-defined nodes, even the phone radio and technology can be reprogrammed, is another way they're going at present, where if we do get another change in radio technology, it may well merely mean a software update to your phone. Finally, getting to the end, is what else is there? Well, there's BGAN, which is something I was responsible for integrating and testing, which is a broadband global area network and comprises of 3 geostationary satellites which provide 3G services, or now and 4G services, to the 8 million odd people that are on a ship anywhere at any one time. So if you've been talking about the terrestrial side and the land-based bits of it, what about the oceans? Well, here's what the oceans are covered by, and each of the satellites has a spot beam which represents the cells, and so you can actually use a mobile phone virtually anywhere on the Earth's surface. The only places you can't get to are the extremes of the footprint in the polar regions, but there are satellites being launched at present to address that. This is a bit about the types of beams these satellites put out. The other thing that my company was finally involved with was a deployment of improved capacity for aircraft, and effectively makes the cell sites on land point upwards towards a mobile, towards the aircraft. And the concept would be to use, if you're flying inside the zone, within the European zone, all aircraft would have an ability to have cell handover between ground-based cellular environment, and when not flying over land, they would switch back to satellite systems. And they can actually, this has been implemented and it has been tested. We were a signatory to it. I don't know how it's going to work out with Brexit, but the phone, the aircraft can actually, and you'll be able to use your phone, I might add, physically. There'll be no restriction on using the phone inside the aircraft, because the phone will be instructed to reduce its power transmit levels to prevent interference with the aircraft systems. But it will be able to attach to BGAN Eurosat, as well as the terrestrial band systems as it flies over. That's the coverage area for that. And gentlemen, I have got to the end, and thank you for bearing with me and letting me overrun. So, is there any questions?
There's been a lot going on since System 4.
Yes, Peter, a lot went on since System 4, yeah. I probably barraged everybody with lots of information. System 4 was hacked to places, yeah.
Yeah.
But you worked on System 4, interesting.
No, I was in security at the time, and the authentication on System 4 was crude, to say the least. In fact, there was no authentication, but they could only block 2048 numbers out of the 5-digit numbering scheme that was used on System 4. So you could basically put a signal up and select any one of those 9,999 numbers, and the system would let you on. And it would only check you against a database which is 2048 numbers. So you could make a telephone call on a completely fictitious number, and you could receive them actually if you told your friends what number it was. And the clever people had to reprogrammable mobile phones. They would program their subscriber number on a thumb wheel switch and just choose a different number every time they made a phone call and never pay for a thing. Mm.
Yeah.
Peter, is the system all two-directional now, so people can talk in both directions and interrupt each other? Because it used not to be so, was it?
No, I haven't restricted anybody. If you can,
no, I don't mean us. I mean the telephone, the mobile phone system. If you're on the mobile phone,
yeah,
on the new systems, can people talk at the same time and interrupt each other, or does one shut the other one out?
What in terms of when you're talking, when you're using the phone towards your head, right?
Yeah.
You have simultaneous transmission in both directions. There's no hybrid involved, so there's no electrical echo from the distant end. Albeit if you have a case of some sort or some device that allows the microphone to hear the speaker, you can get acoustic echo. You can get acoustic echo from in a place with no carpeting. So there is an acoustic cancellation that's usually done in the phone, but when you switch to loudspeaker mode, you definitely are only one direction at a time. It's voice switched because otherwise it would oscillate.
Right.
So as soon as you go into hands-free mode, it's all voice activation. If you go into double talk, if you try to double talk, whoever's got there first dominates until they relinquish.
Yeah, I remember on my previous phone a conversation with somebody, and they talked, well, they made noise continuously, and I was trying to interrupt them and adjust the flow of the conversation, and was totally incapable of it for about 10 minutes.
No, unfortunately, that problem exists. If only because of the delays in speech processing. Despite the speeds we're talking about, there's always at least a 30 to 40 milliseconds worth of delay in one direction. If it gets to the other end and any reason echoes back to the talker, you've got an 80 millisecond round trip. You're going to be inhibited from talking by your own echo, and
right.
Well, you know what it's like with satellite. With satellites, 240 odd milliseconds up and 200. With a geostationary, 240 up, 240 milliseconds down. There's a 480 millisecond round trip delay. That becomes almost. Well, you've seen it on television where people interrupt when someone's talking because they can't work out that they've just said something. That dilemma, unfortunately, is the nature of physics. In terms when we're talking about using satellite, it's getting better because processing power is going up in the phone. So the time to sample and quantize speech in the phone, even be it not done in hardware, but done as a software function, is getting ever faster. And providing you can keep it under 24 milliseconds within a whole network, so the round trip's under 48, you don't need any cancellation and you can have simultaneous speech.
Right. Thank you.
Yeah, the reason I know a lot about, I was echo canceller responsible for BT international circuits, and I used to work with Martlesham in testing and evaluating new echo cancellers to be deployed. I then got headhunted and moved to Ericsson's on working on the first 1800 mobile network in the world. And the first problem that came up was echo cancellers. I thought I'd dumped the problem when I left. And the very problem I identified with BT with an echo canceller was the same problem I was getting with the customer. He said, this is no good. And I worked for Ericsson's and they said, well, you've got to tell him it's okay. And I said, well, no, I agree with the customer. I think the canceller's rubbish. Echo cancellation was a big problem, especially in the early phones. We know with the plastic covers, with the cellophane over the top, the plastic over the top, where the speech could be directed by the case back to the microphone. They were terrible things, which made the thing, not get dirty, but they were a nightmare for echo. Yeah. I think what fascinates me is that ciphering part, which I didn't manage to talk about, which is the actual check-in and authentication, goes all the way back to Lorenz. This exclusive ORing, the amount of exclusive ORing that goes on with bit patterns to cipher speech and data is exactly the same. And so when, I read and got to read about that, and you think, so how did they know? How did we know all this? Well, I know the history now because these people, that's what was going on back in the war, wasn't it? So it was refreshing for me to realise I had never appreciated what I thought was rather a novel ciphering technique was actually quite an old, established and cunning method.
It was old back then. In 1917, it was invented. Well, publicised at least.
Yes, yeah. No, so yeah, I don't know. I just love the museum. I think the museum is the best example of enthusiasm I've come across for a long time. Thank you all for staying with me, and much appreciated. Have a nice Christmas.